Howdy, it's Tubalcain again, and in this video I'm going to show you how to cut a rack. Now a rack is nothing more than a straight gear, and this is the part that I'm going to make. It's a little plunger that goes on this dividing head. Now be sure and go back and look at the other videos that are in this series about dividing heads and gear cutting and calculating of gears and so on, but this video is devoted to cutting a rack. And the pin end of this is broken off, as mentioned in earlier videos, and that's why I have to replace this. So this is a rack, and then up here is the pinion. Now the pinion, of course, is a small gear, and the pinion rides in the rack and moves this in and out, and it turns a rotary motion into linear motion. Every arbor press has a rack and a pinion, and sometimes racks are cut on round stock like this on the one that I'm going to make, but on the larger arbor presses you're going to notice that it's a square ram with teeth cut on it. But everyone that drives a front wheel car is familiar with the term rack and pinion steering, and that is nothing more than your steering wheel connected to the pinion, which is that gear I just showed you, in a manner similar to this. Of course, it's by a long shaft, and as you turn your steering wheel, it's moving the rack one way and then the other way. And on the end of the rack, of course, is a linkage that is connected to your steering wheel, or to your steering wheels, your right and your left-hand front tire. So that's rack and pinion steering. So let's step over to the milling machine and talk about how we're going to go about milling this little rack. Before cutting gears or racks, you need to study up on the subject of gears and gear calculations and all of that. And there's probably 100 pages here in Machinery's Handbook. There's several good pages in the Brown & Sharp catalog. That's an old one. And the Boston Gear catalog. And any good machine shop textbook will cover this also, but study up on it. Before we can cut a gear, we need to identify the gear and the diametral pitch. And the DP, or diametral pitch, is probably the most important thing, and you need to know that so you can determine what cutter to use. Now, how do you find the diametral pitch on an unknown gear? And it's very simple. All you need to do is to mic the gear, determine the exact diameter, and count the number of teeth. And that's what I did in this case. There's 12 teeth, and the diameter is 0.581. And then using this formula here, n plus 2 over d, and n stands for the number of teeth, and we add 2, that's just a constant, over the diameter. So that's 12 plus 2 over the diameter, 0.581, and we simplify it, and we end up here with 24 and change, and we're not worried about the change, so this is a 24 diametral pitch gear. I do not own a gear tooth vernier, but that can be used to measure the teeth, and that would be typically used more when you're ready to cut it and see if your gear has been cut properly. So I'm not going to cover that, but just be known that these are available. This again is a page out of the Brown & Sharp book, but this information is available in many books. But we need to select the gear cutter that we're going to use, and there are always at least 8 cutters in any set of gears for every diametral pitch. So for instance, for 24 diametral pitch, there are 8 gear cutters available. Now I do not have any of those in that size, and some of these are very hard to come by, and they're expensive, so perhaps you might have to spend $50 to $100 for one cutter. So I'm not going to use a cutter, but let me just show you here that we would need the number 1 cutter in the 24 diametral pitch, because that is the cutter that is capable of cutting a gear anywhere from 135 teeth to a rack, and a rack again is a straight gear. If you're cutting a real small pinion gear like the one I just showed you, it would require a number 8, and the number 8 is capable of anywhere between 12 and 13 teeth. So I do not have that set, and I'm going to hand grind my my cutter, which I will show you in just a couple seconds here. This is not the correct cutter to use for this job, but just note that on a gear tooth cutter such as this, there's quite a bit of information, and there's more on the other side regarding who made it, made in USA, high-speed steel, and so on. But this is a number 8 cutter, 20 pitch or diametral pitch, and it will cut anywhere between 135 teeth and a rack. Now, why is there 8 cutters in each set? Because the shape of involute gear teeth vary greatly from the small pinion gears to the larger gears. The geometry on them is totally different and varying in the size, so that's why there is such a big difference. Now, the teeth on the rack cutter are almost trapezoidal, so that's the easy one to grind by hand, which I'm going to show you momentarily. The other ones are not going to be so easy to grind, probably impossible. But looking at this, if you can see that it is trapezoidal. Whereas if we get one here that is a different number, the shape is quite a bit different. And you'll not be able to duplicate that. In these gear catalogs, this is Boston Gear, and this is a really old one, but there's always a page in there to help you identify gears, and there's the profile of the different sizes. And originally I did just match this up with the profile that was the closest, and that of course was 24 right there. And that helped me a great deal too, but I wanted to confirm it with the mathematical formula that I showed you. Now, on the other page here, it talks about pressure angles. Whoops. Pressure angles. That page came apart on me. And the two most common ones for involute gears are 14.5 degrees and 20. And I determined using a protractor like this, holding it up against, and this is a very small gear, it's hard to do it, holding it up to the light, that this is a 20-degree pressure angle rack or gear. The next thing I need to determine is how deep are the teeth on that little gear or that little rack. In most cases, it's going to tell you on the gear cutter. For instance, this gear cutter says that the depth is 0.127, but I don't have a gear cutter for this. So here's the formula, and that's found in the Black & Decker or the Brown & Sharp book and just about any other book. And here's the formula for the whole depth of the tooth. Depth equals, and that's a constant there, 2.157 over the pitch or diametral pitch. So that's 2.157 over 24. Do the math, and the teeth are to be 90 thousandths deep. And that's really pretty simple. And write everything down so you've got it at your milling machine. In another video, I'm going to cover a great deal more about all of the terminology and the different formulas. But for the purposes of cutting this little rack, I'm just telling you the bare minimum. Now, one more thing that we need to know, and that is the distance between the teeth. And that's called the linear pitch. But it's the circular pitch when we have a round gear, but when it's a straight gear, is linear pitch, so really they're the same thing. But the circular pitch is the distance between the center of one tooth to the center of the next tooth. So there's a formula for that as well. And here it is for circular pitch or linear pitch. And that would be P with a little slash on it, equals pi over diametral pitch. So there's pi, and the pitch is 24. So the linear pitch is 0.31. So as I advance my tool from one tooth to the next, I will be moving it exactly 131 thousandths. And there's one other measurement I need. This is a 1/2 inch or 500 thousandths, but it's milled slightly flat here in the area where the teeth are cut. So that has to be done too, and that's during the same operation, but it's just a little bit less, and it's 488. So there's about 12 thousandths that will be milled off to a little bit of a flat. Alright, here's the cutter that I ground, and it's held in just a little bit of a fly cutter that I already had in stock, and that's a 3/16 square high-speed steel blank, about 1.5 inches long, and I ground it at 20 degrees on each side, about like that. And even though it came to a point, then I ground the end of it off so that the end was exactly the width of the bottom of the teeth in the little rack. And I did that by determining with small gauges that the 50 thousandths is what fit right into the bottom of the tooth. So the cutter is 50 thousandths wide at the end. And notice there's appropriate relief on both sides. Now I've already done a sample to proof it, and I just did that on aluminum. And this particular little aluminum rack fit just fine into the slot and into the gear. So I know that that cutter is going to work. Let's take a look at how I ground the cutter. I wish that I had a tool and cutter grinder or a tool bit grinder, but I do not, so I'm using my 6-inch belt sander to grind this, and I have a set of taper gauges of various sizes, and I took the 20-degree one, and I already have it clamped here to the table, and I used this to set the other bar here, which is just aluminum, as a guide. So that taking the 3/16 bit, I could first grind one side and then flip it over and grind the other side until it came to almost a point. Now the table here is set at 5 degrees tilted down, so that gave me the clearance angles that I needed. So after making the setup here, I used just a scrap of soft steel. This is 3/16 key stock. And again, I like to do samples just to see if my setup is going to work. So I did that in both directions. Came out fine. And then I committed myself to high-speed steel. And it worked beautifully. Then when I was done here, I took it to the other grinder and I ground off the end. So it gave me a tool bit that was 50 thousandths wide at the very end. Mounted it in the little fly cutter, and it's ready to use. Okay, I'm ready to cut the rack, but let me talk a little bit about safety first, especially when you're using fly cutters like this. Absolutely no rags anywhere near the machine. That's a no-no. They can get caught instantly and wrapped around, possibly pull your hand in. As a matter of fact, with this, even a brush isn't a good idea. So turn the machine off when making any adjustments. And the chips really fly with this type of cutter, and I'm going to run this at about 1100 RPM, but it's a good idea to wear a full face shield, and I often use this type of shield as well to hold in front of me while I'm examining the tool as it's revolving. So just be careful of all of these things that I just mentioned, and there's always the possibility of the cutter flying out of the holder. So make sure that that's secured properly and that your work is held properly. And notice that I'm in a V-block. The vise is tightened securely. The tool is tightened securely. Set screws tightened. And that nothing can come loose, but with the vibration involved with one of these, just about anything can happen. So just a word of caution. As mentioned earlier, there's just a little bit of a flat spot on the rack where the actual teeth are cut. And I've mic'd that, and there's 10 or 12 thousandths to remove. I've already touched off and fed in that amount in the Y-axis and I'll mill that flat. And that's all there is to it. Now I'm ready to cut the teeth. So I'm going to change cutters and put in the fly cutter, which I have resharpened just a little bit. Touched it up just a little bit since I did the aluminum one. And this is mild steel. It is not tool steel. I changed my mind. I don't want to battle tool steel, and for what this project is, it just really doesn't matter. It's going to last more than my lifetime the way it is. But the sample that I cut, of course, was aluminum. Now if you're cutting tougher steel, you want to take each tooth perhaps in several cuts, but I'm going to cut to the full depth of 90 thousandths on each pass. So let me change tools. There's actually just a little bit more material sticking up out of the V-block here than I would like, but since there's a possibility of me damaging a tooth or so and having to start over, then I still have sufficient stock to redo it. That's why I did that. And I don't want to get too near the vise. And for a small tooth like this, it's probably not all that important, but make sure the work is supported properly. Also, I think now that you can understand that it isn't possible to cut a rack of any length at all on the vertical mill. There's just limited space. So perhaps one, this is 5 teeth, there would be 6 or 8 teeth long, would be the maximum that you could do in this type of setup. But it's just perfect for what I'm doing. It would be certainly easier if I had the right gear cutter and I could just use a cutter rather than having gone through all of this trouble grinding my own tool. Now what I've done off camera here is just swinging the tool back and forth. I fed the Y-axis in until I touched, or a touch off if you will. So now I'm going to back the work out of the way and move the X-axis in 90 thousandths. Remember, that is the depth of the tooth, and I wrote that information down right here. Tooth depth 90 thousandths, linear pitch 131 thousandths. So always do that, or have paper handy with that written down. Do not rely on your memory because you may get interrupted. Now looking at the DRO, I'm only working in the Y-axis, so I didn't even light that up, so there's no confusion. And now I'll feed the full tooth depth of 90 thousandths. And I will lock the Y-axis. And that is done. The actual location of where I start the first tooth isn't too critical, because on the original here, it starts out with about a half a tooth. So I'll cut a full tooth, but I'm going to put this in the lathe and face it to the exact length of the original when I'm done. And I have locked the quill. Make sure you do not forget to lock the quill. And looking at the knee crank here, the dial, I've set it to 0, and the linear pitch is 131 thousandths. So after completing each tooth, I will raise the table 131 thousandths and lock it. And now I'm ready to make that first tooth. I intend to feed very slowly on this so that nothing moves on me, the tool doesn't come loose, and so I won't show the entire procedure, but let me cut this first tooth and see what happens. So far, so good. I've raised the work, or the knee, whatever you want to call it, 131 thousandths, the linear pitch, and again, I always reset that collar on the knee right away to 0, so I don't forget that on the next pass. And I put some oil on it and I'm ready to cut. And tooth number 3, I'm going to raise it 131 thousandths. 131. Ready to cut the next one. I see a little chatter on the cut here, but that's really not going to hurt a whole lot.